Question 17 is an LCR circuit, but it is an LCR circuit in parallel. Actually, you have to study series LCR circuit only. This is connected to parallel LCR circuit. Okay, but you have some idea about parallel LCR circuit also. It's impedance. Okay, parallel circuit, you know, the resistance we take reciprocals. So we can write an equation like this. We have 1 by Z is equal to 1 by R plus 1 by XL minus 1 by XC. So it can be 1 by XC minus XL or whatever, no problem, according to the conditions of the circuit. Now, directly we cannot go for a calculation. So usually we will take them as some vector form and we'll go for the calculations there. We can take 1 by, like that, we will take 1 by Z is equal to 1 by Z square, or 1 by Z is equal to under root 1 by R square plus 1 by XL minus 1 by XC, the whole square, into their product into cos theta, cosine rule, etc. will apply. So like that only we calculate the effective impedance here. Okay, so taking them as vectors. Okay, cosine rule will apply considering all directions, everything. And that way only we have calculated LCR circuit also, you know. We have completed the parallelogram like that. So we will get the value of 1 by Z, etc. But come to the problem. Okay, show that the total current in parallel LCR circuit is minimum at resonant frequency. Okay, gives an idea about resonant frequency and resonance of circuit. Resonance parallel LCR circuit. When source frequency equal to resonant frequency, you are asked to show that the current is minimum. You know, in series LCR circuit at resonance, current is maximum. Here you are asked the current is minimum in this condition. So look at this formula. When XC equal to XL, then this term, the second term is not there. So that 1 by Z is equal to 1 by R. Okay, 1 by Z is equal to 1 by R indicates that, okay, 1 by Z is equal to 1 by R, which means the term which we need to add with that is not there. So in such a situation, 1 by Z is minimum. Okay, because the extra term which we need to add with 1 by R to get 1 by Z is not there. That will be 0 at resonance. So you will get at resonance 1 by Z is minimum. 1 by Z minimum means that implies Z is maximum. So at resonance, Z is maximum. Z maximum means, you know, the current is minimum. So in this way, we can show that in a parallel LCR circuit at resonance, we get minimum current. Then obtain the current RMS value in each branch of the circuit. Okay, so they are parallel circuit. Parallel circuit means we know the voltage remains constant across each component. Therefore, we can calculate like this. First of all, we can take IL RMS, which means RMS value of current in inductor. You will get VRMS. VRMS is given to 230 volt. VRMS divided by XL. XL is omega L. Same way you have IC RMS. RMS value of current in the capacitor. You get VRMS divided by XC. And you have IR RMS is equal to VRMS divided by R. Again, I repeat, in parallel circuit, voltage remains constant across each component. So you can calculate these three values. Now, Next, we can have question 80. A circuit containing 80 millihenry inductor and capacitor connected in series, VRMS 230 volts, 50 hertz powers. Now, what are the quantities to be calculated? First, part A. Obtain the current amplitude and RMS value. So you need to calculate peak value of current and RMS value of current. Okay. So IRMS is equal to VRMS divided by, now it's an LC circuit. So you have to note it's an LC circuit. Being an LC circuit, we can say it is XL minus XC or omega L minus 1 by omega C. Okay, 1 by omega C, because in this formula, okay, R square plus under root XL minus XC the whole square. When R becomes 0, you will get under root omega L minus omega XL minus XC the whole square. You can take the square root and you will get omega L minus 1 by omega C. And once you get the value of IRMS, okay, find the value of IRMS. When you get the value of IRMS, next you can calculate IM also. That also asked in the question. IM is equal to root 2 IRMS. Root 2 IRMS. Come to part B. Obtain RMS values of potential drop across each element. So across each element, what is the value, RMS value of potential drop? Again, we can take just PL RMS. VL RMS is equal to IRMS into XL. You will get the value. Now, VC RMS is equal to IRMS into XC. XC is omega C. So you will get the answer. Now you can see there, there also the answers you have to see. We have applied only 230 volt circuit, but that's not the answer you are getting here for VLMS and VCRMS. But again, I repeat what I have told in question 11. VL and VC are in the opposite direction. You take the difference between VLMS, VLRMS, okay, the magnitude of difference, VLRMS minus VCRMS. Take the difference, then you will get answer 230 volts. What you have applied. Okay. The reason we have seen the reason in question 11. Okay. VL and VC are in the opposite direction. So here applied voltage is a difference between the voltage in inductor and capacitor, just like the difference we have taken in the phasor diagram of LCR circuit. Remember, we have taken VL minus VC. Okay. Now, part C. What is our average power transferred to inductor? Okay, inductor does not dissipate any power, so it is 0. Same for capacitor. And this is a circuit comprising L and C only. So total average power is also 0. Now, question 19 is the continuation. And along with this LC circuit, a resistance of 15 ohm is inserted. So we have inductance, capacitance, resistance, VRMS 230 volt, 50 hertz power supply, omega you can calculate. Okay, so these all just continuation. Now here, what do you have? We know that the only component which dissipates power is the resistance. Therefore, power P is equal to, we can say, IRMS square into R will give power dissipated in the circuit. But the problem, you don't know the value of IRMS. So how do you calculate IRMS? First, you have to take Z is equal to under root R square plus XL minus XC the whole square. Again, you need not worry which one will be bigger, XL or XC, because we are taking square here. Now from there, once you get the value of Z, then you can have IRMS is equal to VRMS divided by Z. VRMS divided by Z, so that you can find the value of IRMS. Once you get the value of IRMS, you can calculate the total power dissipated in the circuit using the formula P is equal to I square RMS, because I have told you already, resistor is the only component that dissipates power in the circuit. Next, question 20. A series LCR circuit, values of LC and R are given. Capacitance is 480 nanofarad. Nanofarad means 10 power 9 minus 9 farad. Then come to the questions. Part A. What is the source frequency for which current amplitude is maximum? Obtain this maximum value. You know you will get a maximum. So for part A, maximum current you will get a natural frequency omega naught is equal to 1 by root LC. 1 by root LC. So omega you can find. Then as it is asked only frequency, you can find the value of nu naught also. Then obtain this maximum value. Maximum value of current also we are asked to calculate. So we can have peak value of current Im is equal to Vm divided by Z is equal to Vm into root 2 VRMS. VRMS is given in the question 230 volt divided by at resonance Z is equal to R, so that the value of Im can be calculated. Coming to part B. What is the source frequency for which average power absorbed by the circuit is maximum? Again, power is maximum when frequency nu is equal to nu naught or omega is equal to omega naught, that resonance frequency itself, which we have calculated already, and obtain the value of this maximum power. Obtain the value of this maximum power. Maximum power we can have okay, P max is equal to Vm Im. For the peak values we will take is equal to Vm. And our actual formula is, VRMS IRMS cos phi is the actual formula. So this Vm we can write as one second. Maximum value. Okay, the maximum value of power we have to calculate. Okay, maximum value of power directly we can calculate, because already we have the value of Im. So we have Im square R. That is it. Im square R will give the maximum value of power. The value of Im we have already. So we can find the value of maximum power. Now come to part C. For which frequencies of the source is the power transferred to the circuit half the power of resonant frequency? For which frequencies of the source is the power transferred to the circuit half the power of at resonant frequency? Okay. Now we can calculate it like this. So that we have P is equal to VRMS IRMS. Resonant condition, so cos pi and all we need not take. Now that we can take VM IM. VM divided by root 2 into IM divided by root is equal to VM IM divided by 2. So what is this VM IM? VM IM means it is the maximum power, the peak power which we have calculated here, VM IM. So this we can write as P max divided by 2, half of the maximum power. Therefore, when do you get a half of the maximum power? Half of the maximum power you will get the values for IRMS. When the current is RMS current, then half of this peak power is obtained. Half of this peak value of current, so we can say peak value of power also. Then, okay, so once again I repeat, when current is RMS current, power is peak power divided by 2, or peak power divided by 2 is obtained for a current which is equal to the RMS current. And for RMS current, what is the frequency? For RMS current, you remember quality factor graph like this. So we have omega naught is taken and this current is taken as I max. And here we have taken two frequencies, omega 1 and omega 2, for which we have taken I max divided by root 2, and that I max means it is nothing but IRMS. Therefore, the power corresponding to IRMS will give half of the peak power. But the question is, what is the corresponding frequency? The corresponding frequency is omega 1 and omega 2. So, for which frequencies means you need to calculate the values of omega 1 and omega 2. Now, how can you calculate omega 1? Omega 1 is equal to omega naught minus delta omega. Hopefully, we have calculated omega naught in part A. Yes. So, equal to, you will get the value of omega 1. Then omega 2 is equal to omega naught plus delta omega. So that omega 2 also can be calculated. Once you get the values of omega 1 and omega 2, you can find the values of mu 1 and mu 2. So from here, you will get the value of mu 1, and from this, you will get the value of mu 2. But again, the problem remains, that is, how do you calculate delta omega? So you need to find delta omega. Delta omega can be calculated using quality factor formula. Quality factor Q is equal to omega naught divided by 2 delta omega is equal to, it is the equation for a quality factor. Okay, quality factor formula we have omega naught L by R. Now omega naught is cancelled there, so that from this equation you will get delta omega is equal to delta omega is equal to 2L divided by R. Sorry, delta omega is equal to R divided by 2L. R divided by 2 L. So from this equation, using this equation, you can find the value of delta omega. Then substitute in these two equations, find the values of omega 1 and omega 2. From omega 1 and omega 2, you can find the values of mu 1 and mu 2. Now come to part D, find the quality factor of the circuit. Quality factor Q is equal to any one formula you can use. Omega naught L by R you can use so that you can find the value of quality factor also. Now come to question 21. Obtain the resonant frequency and Q factor of LCR circuit. Values of L, C and R are given. Okay. Resonant frequency formula is again we have omega naught is equal to 1 by root LC. Resonant frequency can be calculated. Quality factor can be calculated. Okay, Q is equal to omega naught L by R. Again, all values are given, you can calculate. Then, there is a second part. It is desired to improve the sharpness of the resonance of the circuit by reducing its full width at half maximum by a factor of 2. Suggest a suitable way. So, here, again we take the formula Q is equal to omega naught divided by 2 delta omega is equal to, we can use this formula, any one formula we can take for quality factor. Okay, now we will take this formula 1 by R into under root L by C. Now what we have to do, the width 2 delta omega, quality factor graph, we know this width is 2 delta omega. This is a width 2 delta omega. This 2 delta omega, that width should be reduced by a factor 2. That is the question. Now, how can you reduce that width by a factor 2? We have to look into this equation. Is it possible to adjust with L or C? Suppose L. If you reduce L by 2, or you can increase C by a factor 2, but that will change omega naught. Therefore, we can't do anything in the case of L and C. So, what is the only option? You have to adjust with the R. Already in the sharpness of the circuit, we have seen that the width, the sharpness depends on the values of R. If you change the values of R, then you can see the sharpness will increase. Okay, so we have to adjust the value of R. Suppose here R becomes R by 2. The value of R is changed from R to R by 2. Then naturally left hand side of the equation also, the denominator will be varied as 2 delta omega by 2. So width will be reduced by a factor 2. So what would be our answer there? We can reduce the width by a factor 2 by making R equal to R by 2. Then come to question 22. In any AC circuit, is the applied instantaneous voltage equal to the algebraic sum of instantaneous voltages across the series elements of the circuit? Is the same true for RMS value? Okay, instantaneous values. So here we have seen whatever be the situation, everywhere we can apply Kirchhoff's law. So for the first part, answer is same. Okay, it is true. But is the same true for RMS voltage in the components? No, we can see that RMS voltage in certain components. We have seen in question 11, we have seen that. We have seen the same situation in Question 18 we have seen, okay, RMS voltage may be extremely high because of the charging due to the induced EMF, etc. Therefore, the applied instantaneous voltage is equal to algebraic sum of instantaneous voltage is correct for the circuit, but when you take the components, their RMS values may be totally different. Then next, a capacitor is used in the primary circuit of an induction coil. So, induction coil is a circuit that is used to produce very high voltage at all. Okay, so then in that very high voltage, okay, you switch off the circuit. So what happens? The current becomes suddenly zero, and it's a coil. So when current becomes suddenly zero, a very strong induced EMF will be produced, and that very strong induced EMF will produce spark between the terminals. So we know that when you switch on the circuit, you can see a spark. What is the reason? Because between two terminals, the air gets ionized and becomes conducting. So that's the reason electricity that time passes through the air, and being a poor conductor, air gets heated. That is why you see the spark. The same problem will happen here also. When you suddenly switch off the inductor, which is at a high voltage and current, okay, the sudden disappearance of the current will produce a very large induced EMF, producing the spark. So, what can be done to avoid that spark? We have the inductor circuit like this, the inductor, and the question says that in the primary we can connect a capacitor also. So remaining circuit. Here, when you switch off the inductor, a very large induced EMF is produced. That induced EMF will be used to charge this capacitor, so that the problem of spark can be avoided. Okay, so your answer could be like this. When we switch on or switch off the induction coil, a large back EMF is produced. As its magnitude is very large, it can produce the spark. If capacitor is connected in the circuit, this large induced EMF is used to charge the capacitor, so that there is no problem of production of spark. Then next, part C, an applied voltage signal consists of superposition of DC voltage and AC voltage at high frequency. AC at high frequency. The circuit consists of an inductor and capacitor in series. Show that DC signal will appear across capacitor and AC across inductor. Here, the first point you have to see that when do you get a voltage drop? You take the case of an electric circuit comprising a resistor, and current passes through the circuit. When current passes through the circuit, we can see this resistor will give an offense against the flow of current. And wherever there is an offense for the flow of current, their energy will be dissipated and voltage drop will be there. So here also you can see across a resistor there is a voltage drop. That is what we used to say. If a particular EMF is applied by the cell, then you get a voltage drop across the resistor. So to understand the question, you have to understand this concept. Wherever there is an offense for the flow of current, you get voltage drop. Now, take the case of inductor and capacitor. You have Xc is equal to 1 by omega c, and XL is equal to omega L. Now, take the case of DC signal. Already we have discussed in many cases. Capacitor blocks DC, while inductor is an easy path for DC. XL equal to 0 for DC. So inductor does not give any offense against DC, while capacitor blocks DC. And as I mentioned before, wherever you get an offense against the flow of current, you will get voltage drop. Inductor cannot give any offense against DC, but capacitor blocks DC. Therefore, DC voltage will appear across capacitor. Now, take the case of AC. When you take AC, you can see AC having high frequency, so the value of XC is very small, while XL is high. Capacitor is an easy path for AC. Capacitor will not give much offense against AC, while inductor is an offensive path for AC. Inductor opposes the flow of AC. Again, the same point, wherever there is an offense against the flow of current, you get voltage drop. Accordingly, AC is opposed by inductor so that AC voltage is dropped across inductor. Now come to part B. A choke coil in series with a lamp is connected to a DC line. The lamp is seen to shine brightly. Insertion of an iron core in the choke causes no change in the lamp brightness. Predict the corresponding observations if the connection is to an AC line. Okay. The question says that there is a series circuit of a bulb. Bulb means you have to take it as a resistor. Then next it is connected to a coil, choke coil. Now the first case, you can see the circuit is connected to DC. Battery can be connected there. Circuit is connected to DC. The bulb will glow, and at that condition, insert an iron rod. Yes, iron core. Insert an iron rod into the inductor. That cannot make any difference in the brightness of the bulb. What is the reason so? Because in the previous case we have seen inductor has no influence on DC. Inductor cannot oppose. XL equal to 0 for DC. Inductor cannot oppose DC. Even though you insert the core material, the value of inductance will change, but inductor has no role in the case of DC. Therefore, no effect. Bulb will continue to have the same brightness. Now, in the circuit, assume that DC is replaced by AC. DC is replaced by AC. When DC is replaced by AC, what will happen there? You see the situation, XL is equal to omega L. Now, an additional reactance will come in the circuit, that is XL. And the formula for XL is equal to omega L is equal to omega into value of L is mu naught n square L A. Now, in such a situation, okay, bulb will glow with a certain brightness. In such a situation, an iron rod is inserted here. When iron rod is inserted, what happens to the new reactance? XL dash is equal to omega into mu r mu naught n square La. Inductance is increased by mu r times. Value of mu r for iron is around 1000. So inductive reactance is increased by 1000-fold. It will increase the impedance of the circuits. When impedance increases, so we can see XL increases. When XL increases, Z will increase. When Z increases, current I decreases in the circuit. As current I decreases, the brightness of the bulb decreases. Okay, so you can see when the iron rod is inserted and the AC is connected, the brightness of the bulb decreases because inductance increases, impedance increases, current decreases. While in the case of DC, you cannot observe any change because XL is 0 for DC. Then next, why is choke coil connected in the use of fluorescent tubes with AC mains? Why can we not use an ordinary resistor instead of choke coil? You know, there is a choke in this tube which we use at home, and there is a coil of a number of turns. So just in brief, when you see the use, you can see inside the tube the gas is filled and electric discharge is produced in that gas, so that the atoms will be excited to the higher energy level. When they de-excite, the radiation is produced, and that radiation is converted into visible light, so that we will get light from the tube. That is the principle. Okay, so we need a very high voltage uh, to excite these atoms. So high voltage electric discharge is required. So how can you produce high voltage there? High voltage can be produced with the help of choke coil. Okay, you can control the current so that you can increase the voltage. You can see we have a starter there. By a momentary short circuit, this starter will produce a high current which can be converted into high voltage with the help of choke coil. Okay, because a sudden variation in current will produce a very high induced EMF, and that high induced EMF can be considered as a high voltage which is capable of producing electric discharge inside the tube. Now, that is the reason, okay, we need the choke coil in the fluorescent tubes. Okay, the high current produced by a momentary short circuit is converted into high voltage, and that high voltage is used to produce electric discharge. Then, so this is actually produced by the offense of inductor. Inductor will oppose the current through the in the coil. Now, why can we not use an ordinary resistor? Okay, resistor can also produce the voltage too, but resistor will dissipate power. Inductor will not dissipate power. So the action can be done without loss of energy if we use the choke coil. That is why we do not use resistor there. Now, next question 23. It's a transformer. We have input power. Okay, so input power at 2300 volt. That is primary voltage VP. Then step down transformer with the primary winding 4000 turns NP, and the required output voltage Vs is 230 volts. Okay, so what is the number of turns in the secondary Ns we have to find out. Okay, use the transformation ratio equation. We have Vs by Vp is equal to Ns by Np, and from this formula find the value of Ns. Other quantities are given. Now, next, at a hydroelectric power plant, the water pressure head at a height 300 meter. Height is given 300 meter. Then water flow available at 100 meter cube per second. 100 meter cube per second means it is the rate of flow. Then if the turbine generator efficiency is 60%, efficiency is 60%, means 60% of energy is converted into electric power. Okay, take G 9.8. So we can have power formula P is equal to work upon time, and here work we can take as force into displacement divided by time. Now force into displacement, force means it is pressure into area, while S by T will give the velocity. Now again, area into velocity will give a rate of flow. So we can have P into rate of flow can be written as volume per second. Volume per second. Again, we can have pressure P is equal to H rho G. This is pressure. Therefore, power P is equal to H rho G into volume per second. Then out of this much power, okay, this power only 60% is converted to electrical power. Therefore, the electrical power produced PE is equal to 60% of P. So first you find the value of P here, then find it 60% so that you can find the electric power produced. Now question 25. A small town which needs 800 kilowatts power. That is the required power for the town. Now at the town the power is distributed at 220 volts, and the power plant is 15 kilometers away from the town. And at the power plant, the power is generated at 440 volt. The resistance of the transmission wire is 0.5 ohm per kilometer. For 1 kilometer, its resistance is 0.5 ohm. Then the town gets power in the line through a 4220 volt step down transformer. That means the power reaches the town at a voltage 4000 volt. So these are the data given in the question. Now part A, estimate the line power loss in the form of heat. So let's see part A. How can we calculate the line power loss? So we can see here the power required. Okay, the power required in the town is 800 kilowatt. That means 800 kilowatt of power reaches the town. So we use the formula P is equal to VI. P is equal to VI. And how much is the power? Power reaches the town. Town requires 800 kilowatt, which means 800 into 10 power 3 is equal to, and the power reaches at the town with a step down transformer 4220 4000 input. So voltage we have to take 4000 into current I. So from this you can calculate the value of current I. I is equal to, okay, you get 200 ampere. So I is equal to 200 ampere. Now line power loss we need to calculate. For getting line power loss, you should know what is the total resistance of the circuit. So here resistance per unit length is 0.5 ohm per kilometer. Now total, what is the length of the power? The power station is 15 kilometers away from the town. Minimum you have to use 2 wires for the transmission of the power. So 15 plus 15, you will get a 30 kilometer length of wire. Therefore, you can see the total resistance of the transmission wire is 15 ohm. 15 ohm is the total resistance of the transmission wire. Now, line power loss you can calculate. Line power loss P is equal to, okay, P is equal to, it is the line power loss, no confusion, okay. Line power loss is equal to I square R. Substitute the values of I and R. You will get around 600 kilowatt, which means 600 kilowatt of power is lost during the transmission in the form of heat. Okay. Now, part B. How much power must the plant supply, assuming there is negligible power loss due to leakage? Assuming that there is no leakage, then how much power should be produced? So, part B. So, here, town needs 800 kilowatts. During the transmission, 600 kilowatt will be lost. Therefore, the total power generated, if the town needs to get 800 kilowatt, then 800 kilowatt plus 600 kilowatt in the form of heat. So minimum 1400 kilowatt power should be generated in the power station. Then only the town will get 800 kilowatt. Then next, part C. Characterize the step-up transformer at the plant. When we think about the step-up transformer in the plant, we can take like this, okay? So we have the power station. So here, power station. From the power station, the power is supplied. Now, when the power is supplied, I'm going to take the two conditions. The one is symbolically we can represent the total resistance of the line. The total resistance of the line symbolically we can represent as a resistor. Then next, so two wires we have to use. The total resistance of these two wires we can consider as a resistor. And the next load is the town. Is the town. So all the devices in the town. So here the power is produced, transmitted. So total we can consider just like a two devices connected to a circuit. Okay, one is the total wire, transmission wire. Second one, the total town. So whatever voltage produced or transmitted here from the power station will be dropped across the line. Remaining part will be dropped across the town. That is our concept here. Okay, so total voltage, it can be just considered like a battery connected to two devices. Battery will give a particular EMF that will be dropped across two resistances. So here town, the whole town can be considered as a load, means resistor. The whole transmission wire can be considered as a resistor. So two components are there, and whatever voltage is transmitted will be dropped across these two components. Okay, so already we know that the power reaches the town in 4000 volt. So voltage drop across the town is 4000 volts. So what is the voltage drop across the total line of transmission, which you can calculate using the formula V is equal to IR. V is equal to IR is equal to 200. Value of I we have already calculated, and value of resistance is 15. So you will get 3000 volt. So how much will be the total voltage transmitted from the power station? 3000 volt is dropped across the line. 3000 volt dropped across the line. 4000 volt is dropped across the town. So at what voltage power should be transmitted from the power station? It should be 7000 volt. So the power station should transmit the power at 7000 volt. So it gives 7000 volt, 3000 is dropped across the line, and 4000 is dropped across the town. Okay, so we need to characterize the step-up transformer at the plant. Question says that power is produced at 440 volt in the plant, and the power should be transmitted at 7000 volt from the plant. Therefore, the plant needs a transformer 440 7000 step up transformer. Okay, so the plant needs 440 7000 step up transformer. Now come to question 26. Question 26 is same as that of question 25. Only difference is that here we have 4220 step down transformer in the town. The power reaches at 4000 volt at the town in question 25, while in question 26 power reaches at 4000 volt. Okay, and you need to follow all the steps which we have discussed in question 25. Here the difference you can see, you will get current is only 20 ampere, while in the previous question we got 200 ampere. What is the reason? Because power transmission is at a high voltage here. When voltage increases, current decreases. With the help of transformer, we can do that action. Okay. Anyway, so current is only 20 ampere, and when you calculate, you can see line power loss is only 6 kilowatt. You see the difference? When voltage changed from 4000 to 40,000, the loss of energy decreased from 600 kilowatt to 6 kilowatt. So that is the advantage of transmitting power at a high voltage and low current. Okay, then you have to follow the remaining step B and C, and you can characterize, you can find out what should be the primary and secondary voltage of the transformer which you need to use to transmit the power at 4000 volt at the town. Okay, that's all the numerical problems of the chapter. Thank you.